Great. So, oh, got it. All right. So, hi, I'm Noel. So, thanks for inviting me to give this talk. I'll share some of my perspectives on robotic control and kind of how I've been led to thinking about that in a hierarchical fashion. And when we were talking about me giving this talk, it was stated to me that you were really interested in hearing more about control. So I took that as an excuse to throw in a little bit of a deep dive into nonlinear control and some other aspects of control. Okay, so maybe just to set the scene, where are we with the status of robotics today? We're seeing deployment of systems in a way we really haven't, even a decade ago. So Digit in the top left just got employed by Amazon. We have Spot and Animal in industrial settings doing inspection and self-driving cars all around. And so we can now, for the first time, really start to ask systems level questions. Can I complete some task and design a whole stack to accomplish that all the way down to the motor torques? In contrast to before, when maybe 10 years ago, we were falling around and didn't even know how to walk. Okay, so the problem setting that we're going to be focusing on is kind of this abstract one of, let's say on the left-hand side, I'm asking a robot to complete some task. And then I want to design some sort of policy where at the end of the day, I have to send torques to the robot. So I was listening to a talk by Animesh Garg at ICRA, and he had this beautiful separation here of what we're trying to do and how we're trying to do it. So we're going to focus on how to achieve these tasks. And I'm assuming that the semantic level understanding of what we're trying to do has been taken care of. So instead of abstractly complete some task, let's say specifically that has been parsed by your favorite language model and a LERF to give you a goal location and maybe some understanding of your environment and the obstacles in it. So the classical robotics perspective on how to achieve a task like this is to split it up into subcomponents. So maybe first we'll do a high level plan, like a decomposition of my space, giving me waypoints. And then from those waypoints, I'll produce trajectories in a mid-level. And then at the low level, I'll try to track those trajectories, and that'll give me torques. So one benefit of splitting it up in this way is that each level kind of has a canonical model associated with it. So at the low level, I really have to reason about the full nonlinear dynamics of my system, because that's where I'm applying the torque to. And at the mid-level, maybe I have some discrete time but continuous space representation. And at the high level, maybe I have a graph structure. And in splitting it up, I can leverage these different model representations. And furthermore, there's a timescale separation. So at the low level, I have to be executing very quickly for dynamic stability. But at the high level, I probably don't have to reason so quickly about my environment. Okay, so we're going to explore this in the context of some recent work that I did with a hopping robot. So just to give some concrete instantiations of what these levels are. At the low level, we're trying to command torques to spin these motors. At the mid-level, I'm producing trajectories for stable hopping. And at the high level, I'm trying to reason about how I'm interacting with my environment. So this interaction with the environment is something that I'm currently working on. So I'm not going to talk about that very much in the context of the hopper, but we'll discuss it a bit. Okay, so since we'll be using this platform kind of as a motivating platform throughout the talk, let's introduce you to it. So this was designed and built by a previous graduate student in the lab named Eric Ambrose. And so the state of this robot, it's got an orientation and a position, so SE3, and then it's also got 4 additional coordinates of these flywheel angles and then the foot position. So the input, there's 4 inputs. I can control, like I said, these flywheel motors, and then I can also compress the foot. And you'll notice that the number of inputs is far less than the state of the system. So this is a very underactuated system, which means that the control has some complexities, which we'll discuss. And then in terms of compute on board, there's just 2 teensies which are doing the feedback control, and it's communicating over Wi-Fi with this off-board desktop, which I would say is decently powerful. So some of the challenges, like I said, this is highly underactuated. So when I'm flying, I'm basically just following a ballistic trajectory. It has relatively large dimensionality. It has hybrid nonlinear dynamics, and it exists in the space of orientation. So we have to be careful about how we're thinking about these manifold valued states. Okay, so let's take this system in this example scenario. Let's say I'm starting at an initial condition and I want to get to some goal location. And here's a map of my environment, some clutter. And remember, this is a state space of 20. My input space is 4, and I've got nonlinear dynamics. So what's one way maybe to achieve this task? Well, let's take a high-level perspective and maybe do some sort of kinodynamic path planning, some RRT with some refinement at the end. Maybe this was actually kind of hard to do, right? Because I have to reason about the full state, these hybrid nonlinear dynamics, and I have to solve these 2-point boundary value problems or roll out these open loop trajectories to stitch together. And at the end of the day, what do I get? Well, I get a sequence of these open loop control actions. And if I play those forward, I'm probably going to diverge because I'm using model approximations and I've got disturbances at the end of the day. So what would I do instead? Well, what I would rather do is just say, what's the task space that I'm operating in? Well, right here, I'm just considering the plane. So why don't I just consider states in the plane, some 2-dimensional state? And if I had 2-dimensional inputs where I could control the XY position or XY velocity, let's say I have single integrator dynamics, that would be best. And I would just hope that when I pass that plan down, somebody is able to track it properly. Now, the somebody who tracks it properly is me. So we're going to talk about a little bit about what it takes to track a signal like that, why it's even well posed. But if you do this, right, this is kind of a decomposition of the problem. You still might crash into your obstacles or diverge. And that's because the tracking controller that we design is probably not able to execute the plan perfectly. So kind of the whole context of what I'm going to be talking about is that instead of thinking about these block designs in isolation, we need to have a more of a systems level perspective when we're designing these hierarchies. So now if I pass up a representation of how well I can track this trajectory, you can add some sort of buffer to your plan. And at the end of the day, we have some notion that this will work. So splitting it up in this way, but having the communication between the layers, there's 3 points to be made about this. One, it's efficient, right? Because now you can plan on this reduced state space. It's feasible, or has this notion of being feasible if I actually pass up a representation of how well I can track it. And the last point is that if we design this as these independently, then I have a hope of putting a new system in and having it work similarly as long as I design an appropriate tracking controller. So the final point is one of generalizability. Okay, so that's kind of the summary of what I want to talk about. When we think about tackling these complex problems, thinking about it in a hierarchical way is useful because of efficiency, feasibility, and generalizability. Okay, so here we are in phase 1. This is me about to take a deep dive into control. So we'll go through that and then we'll resurface back in the context of these other points that I wanted to make. Okay, so here we are. I'm calling this a quick primer on control. So what's the point of control? Well, I view the point of control as getting systems to do things, right? Or meeting objectives. So here's a system. This is a pendulum that I just found in the lab and took a picture of. So here's a physical system. We're going to start with some mathematical model of the system. So I'll take a state and I'll consider the input. And how are the states and inputs related? Well, they're related through the dynamics. So here I see that the time rate of change of my state is a function of the current state and also the control input that I'm applying. So how do I view dynamics? I view it as a vector field. And how do I view controller design? Well, I'm trying to shape the vector field to have a desirable property. So now we have to have the language of what's a property that I could want my system to demonstrate. So one of them, for example, is stability to a point. This is a classical thing that we would want my system to do. So let's say X star here is the origin that's given to me maybe by a high level planner. And so I want to say I can exponentially stabilize to this point. And here's how I would write that down. I would say the error signal is bounded by this exponential curve. Okay, so this is a statement of what we want to achieve. So now we ask the question, how do I choose a feedback controller to give my system dynamics some desirable property of stability, to shape this vector field in a desirable way? So one way to think about doing this is, well, we have the expression right here. Let's solve for x of t in terms of u of t. And maybe I'll get a condition of what U of t should do in order to satisfy this specification. Now, as a little exercise, let's try to think, what is x of t for the pendulum? And spoiler alert, you can't write x of t in analytical form as a function of u for the pendulum, right? Even for the simplest system, I can't write it down. There's ways to approximate it, sure. Locally it's like a sinusoid, and then maybe I can do some sort of like approximate trajectory for it. But at this level, we're focused on precise statements. What can I guarantee about the system? And so if we can't write the solution down, what hope do we have of saying that we'll meet some stability criteria? So this is where I think there's some beauty here in what's called Lyapunov theory. So this statement of exponentially stabilizing to a point is true if and only if there exists some positive definite function that meets this decreasing derivative criteria. So a way to think about this, let's say for the pendulum, I can think about a generalized form of the energy of the system. And if I know that I'm decreasing in energy, then, fill in the blank, I know that at some point I'm going to converge to the origin. So there's a little bit of a step there that we want to talk about. But what's the intuition for why these two conditions are related? So I'll present just a little bit about this. So on one hand side, we've got the dynamics of the system. So these exist in my state space. So let's say this is a dynamical system and I'm doing analysis now. So I've got my dynamics. On the other hand side, I've got this positive definite function, and I'm considering the gradient of this function, right? So the direction of steepest descent. And the question that I'm asking by evaluating the time derivative of v, so what is v dot? It's the inner product of this gradient field and my dynamics. So I'm measuring the extent to which these two vectors align. Now, if there's 0, it means that these vectors are perpendicular. And what does that imply? It implies that my dynamics are going to take me along level sets of this function. If it's negative, then this is going to be an obtuse angle. And that means I'm going to be decreasing on my Lyapunov function. And if it's negative by some degree, right, minus gamma v as we saw, then I know I have some rate of convergence down. So this is the intuition about why Lyapunov theory works in the way that it does. So the nice thing about this is we no longer have to reason about solutions of my system state, which we know are quite hard or difficult to write down, impossible to write down analytically. But instead, we're looking about the projections of solutions or the projections of the vector field properties onto the scalar valued function. Okay, great. So now all we have to do is find one of these Lyapunov functions, and then we're good. So this is, again, challenging in practice, but in certain contexts, there exist constructive ways to produce these Lyapunov functions. So let's talk about that just for a moment. So let's say we have a desired trajectory. What we can do is define some error coordinates. So if I could define an error coordinate of x minus x desired, then I would know I would stabilize my system state to x desired. Now, there exist quite strict conditions on which outputs are valid. And we'll talk about this in the context of the hopper. But just know for these defined error coordinates as some output of my state minus some output of this desired trajectory, as long as they're valid, and we'll talk about that again, then I know that there exists a feedback controller, and I can write this down. This is just, I'm going to consider the error dynamics, which is going to include my state dynamics, and then I'm going to cancel my nonlinearities and instead put in some stable linear system of my error coordinates. And once I've done this, we can construct a Lyapunov function certifying the stability of these error coordinates just as some quadratic error form. So one nice property also of thinking about it in this way is we have a notion of graceful degradation. So now if I have disturbances entering my system, I can use the same Lyapunov function to state that instead of converging to my point, which is probably too strong of a statement now that I have disturbances, I can converge to some neighborhood of my point. And what this means is that under this feedback controller, and so I said there is we have an existence of one feedback controller, but there's probably a whole class of feedback controllers which demonstrate this property. This is just a proof of existence. But now under these feedback controllers, I know that the solution is going to remain inside this set. Okay, so in the context of what we talked about of wanting some sort of representation of how well we can track trajectories, we have a constructive way to discuss this now. Okay, so now we're experts in nonlinear control. Let's plug the pieces together. Let's take the plan that we got from the high level and let's just track them. Okay, so let's do this for the system of interest, the hopping robot, and let's see what happens. So the high level objective is just to stay where you are. Okay, it's maybe not quite a high level objective, but that's what we're taking it to be. And I'm starting with some sort of error in my initial state. And I'm just using feedback control. And we see that the hopper starts to diverge and goes to the right and is unable to go back to the original position that I wanted it to go to. Okay, so this kind of counters what I was talking about. We said, okay, well, we can track trajectories, but now it seems that we're unable to do this. And the statement of why that is kind of goes along my perspective on why low-level control is not enough to achieve this task. And it's in exactly what I talked about of these construction of which error coordinates are valid. So if we look at the hopping robot, I have actuators to control the orientation. But when I am in the flight phase, when I'm in the air, I cannot control the lateral position of the hopping robot. So this means that my control input has no effect instantaneously on where I am in positional space. And because this Lyapunov condition is an instantaneous condition, I cannot choose this XYZ position as a valid output. Okay, but I have actuators, so what can I do? Well, I can choose the orientation to be my desired output, and I know I can converge the orientation exponentially fast. But then after some finite time, because I'm converging exponentially fast, but not in finite time, I'll have some error when I hit the ground. That error will propagate, and that'll lead me to start diverging. All right, so to summarize what I just said, output stability is not the same as full state stability. And this really comes to head in the context of underactuated systems, when I care about stabilizing my full system state. Now, another limitation of just having low-level control is that we did not reason about input constraints or state constraints. And so when I said, oh, there exists this controller where I'm canceling my nonlinearities, that might take arbitrarily large torques. But for this system, for example, there's a maximum torque I can apply. So how do we reason about state and input constraints? And how do we reason about stabilizing the full system state? Okay, well, this motivates the introduction of a mid-level, right? How do we do intelligent trajectory design? So now I'll talk a little bit about model predictive control in the context of how it was used to stabilize this hopping robot. Okay, so what is model predictive control? Well, I take my model and I predict how my current control actions will affect my future state. Okay, so as opposed to having these instantaneous convergence conditions, now I'm planning over a horizon. How do I do that? Well, oops, this bar is, let me move this bar out of the way. There we go. I solve this finite time optimal control problem. So I'm solving for a trajectory, a state and input trajectory in time, which minimizes some cost, subject to my nonlinear hybrid dynamics, satisfying my state and my input constraints. And that starts from where I am. What do I do then? I apply the first control action along this trajectory. And then to get some sort of closed loop performance, I replan. Okay, so the first part of MPC is the model. So let's just discuss the hybrid model for the hopping robot. So I have a flight phase where I have these continuous time dynamics. Then I go through a ground impact where then I have, so my foot velocity goes instantaneously to 0. So I've got this jump in the system state. Then I have some ground dynamics. Then, so those execute quite quickly. And then I hit the hard stops of the robot and I enter the flight phase again. So this forms 2 cycles on this hybrid graph. So when we're planning, we have to plan over this full hybrid state. And the reason we have to do that again is because when I'm in the flight phase, I can't control the position of the system. So I have to decide what orientation should I be in when I strike the ground, which means we have to plan through the strike of the ground in order to determine what I should be doing in the intermediate steps. Okay, so just maybe a little bit quickly, how do we structure this problem of model predictive control? So I've got my dynamics, these hybrid dynamics, but as I stated, this finite time optimal control problem is infinite dimensional with these non-convex constraints. So we have to use model approximations. So what can I do? Well, I can linearize my system dynamics around some reference trajectory and then discretize. And so now I've got this discrete time linear system that I can use for planning. So there's one issue of what I talked about, especially in the interface of how this model predictive control layer goes into the low-level controller. So the low-level controller requires dynamically admissible trajectories. But because there's this space of orientations that the hopper lives on, if we just approximated that constraint of this orientation manifold, I would get states that leave this manifold constraint, and they would not be admissible when I pass them to the low-level controller. So part of the effort of this was phrasing MPC in a geometrically consistent way in order to make the interface between it and the low-level controller sound. So just in pictures quickly, how do we do that? So if I have some reference trajectory that I want to linearize my system dynamics around, I can pull the start of that trajectory back to some identity element, like the identity orientation. And then I can use what's called the log operator to get me into a vector space. So now I've taken this state that existed on a manifold, and I'm in a vector space now where I know how to take Taylor approximations. I know how to approximate my system dynamics. I can solve for a trajectory in this vector space, and then I can project it back onto the manifold. And this is locally a bijection. This projection operator is exact. Okay, so those are the pieces of how we phrase this in a geometrically consistent way. So now the decision variables of MPC for this hopping robot are the full system state, including these geometrically implicit states. And what do? Well, I phrase this now as a quadratic program. So I have these discrete time linear dynamics where if I expect to have a contact, I satisfy the discrete time update. If I am in the flight phase, I have this continuous time update. And I do what's called the sequential quadratic programming approach, where I sequentially linearize, discretize, solve the QP, and then iterate. Okay, so that's just a deep dive into the control architecture that's running on the hopper. The final point is that for approximating the system dynamics, I use the Pinocchio open source package. And for solving this quadratic program, I use a tool called OSQP, just for those interested. Okay, so what's the result? Maybe we said we like robot sounds, so I don't know if that's coming through, but the result is that we can get stable hopping on the hardware of this robot. And here it just, I'll just play it until the end so you can see. The foot stopped after 50 hops. We can also show this method off in simulation, where now I can switch off the torque limits of the system so it can hop, a meter in the air. And we can see that this demonstrates a very good ability to reject disturbances, right? So as opposed to it hopping off just with the low-level controller, now the coordination of the mid-level and the low-level controller is able to stabilize back to the system state. And so now here's what we're doing in this segment is we're tracking a trajectory. So let's say these are waypoints that were given to me by some high-level planner. Now I have this ability to track those waypoints, and I can think about interfacing this with a high-level planner. And so what we can see here, these yellow dots are exactly the center of mass over the horizon, and this red dot is where I want to be. And then lastly, because we phrase this in this geometrically consistent way, we can explore the space of orientations and do flips on a system. So that's a fun little result as well. Okay, so that was a deep dive into this block of low-level control and this block of mid-level control, especially in the context of the hopper. But now I want to take a step back and present this system-level perspective of hierarchies, right? So when people are doing the design of algorithms, they're embedded in these individual levels. How do I construct a feedback controller which is able to track? How do I construct a good mid-level controller? But I think a lot of the interesting questions here are, how do I interface these pieces together? And if I think critically about the interface between these pieces, what do I get, right? And the points that I want to make and reinforce are, I get notions of efficiency, feasibility, and generalizability. So let's explore those in the context of these hierarchies now. Okay, so this is a very simple result in the context of efficiency, especially in the interconnection between MPC and a low-level controller. So here is a linear discrete time system, and I have bounded additive disturbances in the form of just some polytope. This W exists in some polytope. So if I propagate my state forward from some initial condition, I'm going to end up in some uncertain state. So I have where I predicted to be plus this disturbance set that I could experience. So what would I like to do? The way I'm phrasing it now is, if I just have MPC, then I need to plan what my control action should be in this uncertain set. So I should plan what my control action should be everywhere in this set. So a nice result here is that instead of, for this linear system, instead of planning it over this entire set, I can instead just plan it on the vertices. That seems convenient, except if I propagate again into the future, this vertex count is exponential in the horizon length. So that means, as stated, with just MPC alone, this is going to be an NP-hard problem to do disturbance robust MPC. However, if I incorporate the use of a low-level controller, where now this is my set omega that we talked about before, this is like a tracking invariant, where I'm passing up a representation of how well I can track. Now MPC can plan on the deterministic system. MPC does not have to take care of the disturbances. That's being taken care of by the low-level controller. So in terms of efficiency, I have this load sharing between the levels because I'm using them in coordination in a hierarchy, and I'm acknowledging that they're going to be used in a hierarchy. Okay, so let's say I like using MPC in coordination with a low-level controller. The next point to be made is, how do I guarantee feasibility? And also a subtle point here is that I can use this concept of hierarchy design as a design tool. So I know that what's being passed into this entire structure is a goal location and some representation of my environment. I know I have this low-level block that I like, the MPC with a low-level controller. So how do I think about designing a block up here to fit this entire picture and give me a context of guaranteed feasibility? Okay, so this is something that I'm working on at the moment, so I'll just go through it quickly. So what is an assumption I'm making in MPC? Well, as good as my MPC program is, let's say I have the hopping robot. If I tell it to hop 100 yards to the right, and MPC has a horizon of 1 second, right? That's what it was used for that system. There's no way it's going to be able to achieve that task. So the assumption baked into MPC, especially if I have hard constraints on the terminal state, is that I can reach that state in my fixed horizon. And so a way to remove that assumption is if something is giving me states which I can reach, right? So I want terminal states of MPC. And what can MPC represent? Well, I can pass up, which states can it reach within one horizon. So another assumption of MPC is that I have an efficient representation of my state and input constraint set. And what I mean by that is, like, really what I want is a convex representation of my state constraints, for example. So with that in mind, this is what MPC wants. Let's design a tool which is able to give me some sort of convex decomposition into convex sets with waypoints that I know are reachable for MPC. So here's just a pictographic depiction of how you would do that. So I've passed up a representation of the reachable set of MPC. I can decompose my state space into these reachable sets. Now, at the high level, which is what we're talking about, I can think about this in terms of a graph, or a graph of convex sets. That's what GCS stands for. I can solve this graph search problem, and I know now that these intermediate states are going to be feasible for MPC. And this guarantee of feasibility came exactly because I'm having this bidirectional communication between the levels of the hierarchy. So I can pass this plan down to MPC, which can refine it, and then I can track it with a low-level controller. Okay, so that was efficiency, that was feasibility, and now to the context of generalizability. So we discussed the design of these controllers for this system, right? I have some low-level controller, which is stabilizing my orientations. I have some mid-level controller, which is stabilizing, giving me dynamically stable trajectories. But one notion of generalizability is that because I've done this in this structured way, I should be able to translate this to a new system. So here is a new robot using a very similar architecture, some low-level controller stabilizing what I can actuate, which is my joints, the same way that I could actuate my orientation for the hopper. I have some mid-level, which is running nonlinear MPC at the same time scale of 100 hertz. And then this high level, again, it's something that I'm working on right here. It's just a user command, like walk forward. So here's a demonstration of, again, a very similar methodology, but applied to a new system. So here we see the horizon, the forecast of MPC. Here's the forecast of the footsteps. And this is as we disturb the system, it's able to stabilize dynamically. So it's adjusting its footstep length to account for these disturbances while trying to track this user command of walk forward at a specific speed. And then we can also show this on hardware. So we said we like robot noises, but there's a voiceover in this video, so I'm not gonna, the footstepping is quite compelling. You can hear it in the video. But anyways, here's the same method of nonlinear MPC applied to this walking robot now. So I should say this is a planar walking robot, so it can't fall out of the plane, but it still has to step forward and backwards to stabilize itself. And we're working on extensions of this to a 3D robot now. Okay, so in the context of what I talked about, I talked a lot about model-based methods for designing these controllers. And maybe a question you should have is, do I think that these work well? Or do I think that these are generally extensible? Or what are the issues with them, I guess? So here's some failure videos of when it didn't work so well. And what's one of the problems with this? Well, the model of this robot, which I assumed I had, and I actually leveraged to make all of these statements, is not so good. It's got these harmonic drives, which are, the model of the harmonics are temperature dependent. As the grease warms up, I have different properties. This is a nightmare to model. So how do we think about that in the context of these hierarchies again? Well, another point to be made of generalizability is once I've specified this input-output structure, I can use different methods in the same way, right? So that's useful because I can think about problems in isolation as long as I understand their context. But I can also structure what happens at each level, right? So if I wanted to replace, let's say, my graph of convex sets with an RRT or something, I know what the defined input-output structure should be. I know what my expectations are, and I can use that, one, to design the algorithm, two, to use as a debugging tool, right? I'm basically making formal statements about what I'm assuming that this block wants and what I can guarantee from the block. And so now, how do we think about this in the context of, let's say, learning? So I said that we had a poor model. And so the first response should be, okay, well, why don't we learn the model? So this is where learning might be beneficial to include in the hierarchy. But I think the converse statement is true as well, which is that the hierarchy is useful to structure the learning problem. So here's one way we explored this. So again, I said the model of this biped is quite poor. So what did we want from the hierarchy to begin with? Well, we wanted to be able to satisfy these certificates of performance. So here I have an example of a certificate. I'd like to converge to this set and stay within this set in the same way as we wanted to converge and stay within a set for Lyapunov. So I'm going to pass this certificate into some learning problem where the loss function of this learning problem is exactly going to be whether I satisfy this certificate or not. And then because I've phrased this in a way that uses learning, now I can roll out the policy on hardware. I can collect data, compare it to my model, train a residual, and then I can fold that residual back into the learning process. This is this symbiosis of, the learning improves the hierarchy because I get better model information, but the hierarchy improves the learning because it adds all this structure to it. And then, let's see, maybe I'll just play this and talk over it a little bit. So here we just have this certificate violation spatially, and our loss function is the spatial integral of this violation of the certificate. And so here's the initial policies, which don't walk at all. And we see, we love seeing training curves go down. So as this training curve goes down, here's the time varying loss function. Eventually, we get walking as kind of this emergent behavior from satisfying the certificate that we wanted to. And so at the end, here is the trained policy. This is running a neural network to walk in simulation. And then, so now when we deploy it on hardware, well, we see the initial pass kind of doesn't work so well. It's falling forward. Okay, well, we used a model in our training process. So let's collect the data. Let's fold it back into the learning process. And let's retrain a policy now with this hardware data. So here's one episode of hardware data folded back in. It's able to walk stably, but it has quite this aggressive motion. So let's do it one more time. And when we fold it back in again, what we see, we're able to get quite dynamically stable walking. Okay, let's see. Oh, no, never mind. It's a voiceover again. The thuds are quite good of this robot. Okay, so just to conclude here, we talked about this complex problem of passing in some sort of task specification or some semantic information and outputting some trajectory in time. And the statement that I'm trying to make is we should look at the structure that exists in the problem. And specifically, we should look at the communication between the blocks of this hierarchy. And if we do that, we have a separable problem. And we get these notions of efficiency, feasibility, and generalizability in this approach. So hopefully I've convinced you of that at least a little bit. And I just want to thank you for inviting me, for your attention, and also to all the people that I collaborated with on the different projects presented here.
Yeah, thank you for your talk. Let's open up the floor for questions, either in chat. I had a quick one. That last video where you said you folded in the data back. I'm assuming you collect data. So like the one where you said the robot is sort of aggressive, I'm assuming you fold that data back.
Right.
I see. So if you were to continuously iterate, I'm just trying to get intuition on why that sort of refines the walking gait. Is that because like your aggressive motions doesn't satisfy the certificate that well, and then once you train on that data, able to refine the policy? I'm just, could you
exactly. So when I say I'm back propagating the loss of this, I'm going through the model in order to back propagate the loss. And so if my model is bad, then probably when I deploy it on hardware, I'm not going to satisfy the certificate that I wanted. And so there is this time delay also that I think you're commenting on, which is that if I train the policy and then I collect data and then train a residual and then pass it back in, now when I deploy a policy, my new policy is going to be kind of different from the data that I collected. And so we just did it a few times and saw that it resulted in good performance that was able to satisfy the certificate. But I think it's interesting to think about the context of when you would expect that to work or not. Yeah.
I see. Thanks. Yeah. Yeah, I really like this talk because I think the optional theory is coming up more and more recently. So really appreciate you help coming in to talk about this.
Sure. Yeah, and if I should say, if you have further questions about it, please reach out to me. I tried to keep it a little bit high level, but I had to restrain myself from going into the details. I really love the details. So, I mean, send me an email and we can talk about it more.
I had a quick question. So, did you try doing the incorporating learning with the hopper?
Good question. Okay, so
just because I think if you're trying to satisfy the certificate, then you need to sample from that state space where it has not come across the certificate or it has gone across the Lyapunov stability conditions. find those counterfactual points and then put it back in your data. And now you said that your dimensionality of your output space in the hopper is too big. So I was wondering.
I am so glad that you made this point. Okay, great. So I guess two comments. One, if I claim that it works so well, why do we need learning if the model-based approach is working? And there's a point here, which is, let's see, I'll actually turn the video, the sound up again, and we'll play it, and then we'll talk about it. So if you listen to the high-pitched squeal that's coming, and you notice the flywheels, and okay, it sounded like a jet engine taking off. So what happens? Well, I'm assuming I can apply a torque on these motors, but at a certain speed, I saturate the actuators and I can no longer apply a torque. And so there's this very weird behavior where after 30 seconds, I get this screaming of the actuators and then I can't hop anymore, basically. And what's a way to resolve this? Oops, sorry, I'll close this email. Okay, I'm gonna just motivate this by, let's say I'm hopping to the right. I'm applying a constant torque to the right. That means that I'm always increasing the speed of the actuators in one direction. And after a certain amount of time, that's gonna saturate. So you can imagine the hopper is hopping to the right, and then it spins 180 degrees and then continues hopping to the right to spin down the actuator. So this is a very complex behavior that would be difficult to encode in these horizon-based planners, I think. And so I'm interested in exploring the use of learning as a way to design a policy that's able to kind of emergently demonstrate a behavior like that. But the dimensionality is high, as you said, right? So this is a point that I didn't make, and now I feel like I can. So, okay, what's the best slide to make this point on? So what's the input to the mid-level controller? It's the XY position of the hopper, right? What's the output? It's the certificate of how well I can track that XY position. So what was it for Amber? It was basically a lateral velocity, so a lateral position of velocity that's two-dimensional. And the certificate was how well I could actually achieve that, right? So this policy was a mapping from this low-dimensional space into whatever my low-level controller was taking. So when I said sample the state space, it wasn't actually sampling the entire state space. It was only sampling the space that the block of the hierarchy higher up cared about. So if I were to use a similar perspective for the hopper, I would only need to sample this two-dimensional state space. Like I need to come up with policies that, depending on how I'm going, well, I should say four-dimensional, in my XY position and my XY velocity, come up with an appropriate orientation to stabilize me. That's kind of what the mid-level controller is doing. And I can pass up a certificate of how well I can do that. So by baking in this hierarchy, we also get this nice model, this dimensionality reduction.
Mm-hmm. Yeah, that works very well with the architecture that you're proposing as well.
Yeah, nice. Thanks for the question. I'm glad I could make that point.
I had another question. So recently I've been seeing works mostly by Mani Ghaffari's group, where they're trying to model error dynamics on the groups, Lie groups specifically. And they're trying to kind of find linear error dynamics such that they don't have to approximate the linearization across the stability point. So I'm wondering if when you try to make this approximation for this nonlinear control by linearizing it, do you face any difficulties when it comes to, let's say, working on robots directly when you try to roll out your simulation on hardware?
Yeah, good question. So I'll make one point about the geometry and then one point about the approximation of the dynamics. So the point about the geometry is that if you're careful about how you phrase this problem, you do not have to make approximations of the geometry. I can do this in a geometrically consistent way. By instead of considering the existence on this Lie group, I can project it, but project it exactly, there exists this bijection to the Lie algebra, which is the vector space. So I can do this process exactly and keep it constraint implicit. Now, for the dynamics, I have to approximate the dynamics. And I think there's a really interesting question here of, so I wrote down this linear discrete time approximation of finite dynamics, which I know is in some way approximating these, but is not exactly. And so the question of whether this will work or not is dependent exactly on how well the low-level controller can track approximate trajectories. So I can do this analysis where, okay, I have some approximate trajectory I'm sending down, and I have a representation of how well I can track those approximate trajectories. This at least provides a language to analyze whether you satisfy that property or not. Okay, now you asked an empirical question. Do I notice difficulties on hardware? So in the approximation of the dynamics on this robot, yes, there's difficulties because, well, there's difficulties in the dynamics themselves. The approximations, I'm not sure how much additional error that's causing to the system. I think actually because we're running this at 100 Hertz, the approximation of the dynamics is not necessarily the issue. It's the representation of the dynamics themselves. And similarly, we're able to run the approximation of the dynamics at really high speeds now. So I think maybe that those local linear approximations is not necessarily the issue. But thinking about whether that's justifiable or not is a very interesting question, especially in the context of how these two blocks interact.
Mm-hmm. Makes sense. Thank you.
Thank you. See, there's some chat, I'm not sure. Oh, thank you.
All right, well, there's no other questions. I think you already mentioned, if we have any further, come up with anything else later on down the line, to send you an email, right?
Yes, please do. I should have put my email somewhere on the slides. I guess I didn't, but you can find it online. I'll just put my name up again so you can Google me if you have questions. So yeah, here's my name. Send me an email. I'm happy to talk about this stuff. So
perfect. Yeah. Thank you so much again for coming and giving your talk. We really appreciate it. And yeah, let's wrap it up.
Yeah, thanks for inviting me.